So we have a second order system, and we can write the time response of the second order system after plotting the inverse Laplace transform. Or sorry, after taking the inverse Laplace transform. And once we've done this, there are three major components. So we have a scale factor here that tells us what the scale of our response is going to be. We have an exponent that tells us how fast we're going to decay to our final value. And we have a sinusoid that tells us how we're going to oscillate until we get to that final value. And so, I'm interested in finding out, for the time response, what will the limit be if I try to take my frequency of omega n and take that frequency to 0. So that is, I sort of want to take omega n and get it smaller and smaller and smaller so that I'm not oscillating. So what's that going to look like as I get closer and closer and closer to the real axis? So let's take the limit as omega n approaches 0 to see what we get. Well, we'll have this same ratio here. We'll have the value for the exponent that's going to also decay, and we'll have the sinusoid that will sort of go away. So this will eventually be equal to 0. As my omega n approaches 0, I'll get no response. So as omega n goes away, you can actually see this if you look here. So as I set omega n equal to 0, my h of s will be 0. So it's not really a big surprise. But what if I'm interested in omega n being really, really close to the real axis, right? So if I have two poles here, and I want to have those poles actually get smaller and smaller, they're going to get closer and closer to the real axis, but they won't actually be there. So what will my system response be then? Well, if I choose this value to be really small, I'm actually going to get just a really small value. So for small values of omega n, really, really small, then the sine of a small angle is just equal to the small value, or is just equal to that small angle. So now I can rewrite this as this exponent times the ratio, which it's actually divided by 1 minus zeta squared square root. So those are going to go away. And I'm going to end up with this time-valued function. So this is going to be h of t for very small omega n. So again, I'm still going to have this exponential term that's going to make me decay. But now I'm also a function of time. So as time gets bigger, I'm going to accumulate more value, but I'm also decreasing the exponential value. And I'm scaled by the natural frequency. So, just how small do we have to be in order to see something here? Let's look at the next page. So I've gone ahead and drawn a graph here of the response h of t, and we're graphing this with respect to time. So I've chosen arbitrarily for zeta to be equal to 0.7, and I'm going to plot several different versions of the step response depending on different values for omega n. So the first value that I've chosen is omega n is 1 times 10 to the minus 6. So you can see that this sort of looks like a step response. But as we look at the scale of t, that is the actual values that we're plotting for t here and how big they are, you're going to see that this doesn't actually behave exactly like a step response. So if we choose omega n equal to 1 e minus 9, so now we're talking about 1,000 times smaller than the previous, we see that we sort of have a step response, but there's a little bit of a damping here. So we have a little bit of overshoot, and then we come back down and settle at 1 when we provide a step input of 1. But if we look at the time scale, that is, how long does this actually take to happen, it's settling at about 1 times 10 to the 10th seconds. So for a really small value, really small value of omega n, we eventually get our step response, but after 1 times 10 to the 10th seconds, which is a really long time. So what if I now choose omega n of half of that, so 5 times 10 to the minus 10th? Well, I get a response that takes just about twice as long to peak, but takes a little bit longer to decay. And I can do the same thing for about half of that value. And now I'm looking at a quarter of the value of the original omega n, 1 times 10 to the minus 9th. So we can take this to be even further and see that if we're looking at 1/10 of the value, now we're still seeing a ramp that will eventually decay after it overshoots. But we're now talking about 4 times 10 to the 10th seconds in order to actually peak, and maybe 6 times 10 to the 10th seconds until we're actually at our final value. So one thing that I do want to point out is that the overshoot is the same for each of these omega n's. And if you'll remember, that's because our percent overshoot is a function of only zeta. So we don't have omega n as one of the factors in our percent overshoot, only zeta. So we're always going to get the same amount of overshoot. It's just a matter of how long that takes.